All right, we're ready to jump into chapter 6. You can go ahead and share my screen with you. So let's jump into this chapter, biomedical science. So, of course, after studying this chapter, you're going to be able to recognize basic components of the computer system, demonstrate basic word processing, internet and email functions, apply computer knowledge to save patient care, apply electrical safety precautions, cite the basic principles of electricity and their application in the operating room, interpret basic concepts of robotics as they're getting more and more popular, analyzing the geometrical concepts of robotics and the mechanisms of the robotic system. Apply the principles of robotics to save patient care, practices in the OR, demonstrate principles of sterile technique during robotic surgical procedures. So let's jump right in. At the very beginning of this chapter, let me stop the sharing, make sure it's completely sharing. At the beginning of this chapter is this case, and just as we talked about tonight, I want you to be sure you're reading these cases in the beginning as you look at the objectives that are in this case, in this chapter, reading those, being prepared to learn about that as you read the chapter. I want to make sure that you're reading this chapter. Really, so sorry. It's after 10 o'clock here. But during an open colon resection, the surgeon encounters a bleeding vessel. A cryo hemostat is clamped onto the vessel to stop the bleeding while the surgeon is holding the clamp. The CST applies the tip of the activated electrical surgical pencil to the hemostat to coagulate the vessel. Suddenly, the surgeon pulls her hand away, yelling aloud. Upon examination, she discovers a pinpoint third-degree burn on her right index finger. So as you go through this, I want you to be thinking about these questions, where the tip of the pencil should be, and the benefits that could cause the burns, complications that would result from the burn injury, and what's that insulating material in the situation. So we'll be looking at some of that information. So we're going to look at computers, information technology, electricity, and electrosurgery, and the robotics. Talking about hardware, so there's a lot of hardware that you'll see in an operating room, as far as, because things are becoming so much computerized, because we're looking at, there is going to be a CPU in the OR somewhere. These days, computer systems are much more portable, especially in an OR where not especially in the OR, just in general. And then in the OR, they may be a little more stable just because the circulator is moving around and having to stay in outside of your surgical field area, that safe square. And so it just depends on the facility. You're looking at specialty, they may be a little more on that mobile side. So there's a tower, as we all know it, that CPU, a monitor, modem, and then some memory storage devices. So sorry. Using the computer, you switch it on, start it up, log in, all of that. You all are super familiar with computers, how to use them. Of course, the desktop is the first thing that's going to pop up on the monitor screen. And then programs that operate the computer system. These are all the softwares, the individual hardware components, user programs, available on the CD-ROMs or the internet. There's many varieties of different types of software. Word processing, these, we're going to look at the book itself, go into, what was that table, 6.3 and 6.4. So looking at these are the key words, of course. Let's get to the computer page in the book. There's your tower, there's your monitor, there's your keyboard, mouse. hardware. So you're going to be able to read through this really quickly and get a really good understanding of it as well. So here we're looking at the basic of a computer. You know, you've got your taskbar across the top, opening a program, opening a document, you know, click on the title of it to open it, changing the desktop, you know, using the control panel. And those, depending on Macintosh, you know, you've got those preference panels. And then open panel across the top of a PC. Getting help, you know, there's different help applications on both a PC and a Mac. Shutting down the computer, there's shutdown processes that occur, close all the files to shutting down the computer, minimizing and maximizing. You know, think about we're talking about a facility computer, not your home computer. You know, minimizing, maximizing, there's buttons that let you minimize and maximize a window or document. It can be made smaller on the screen. You can open multiple windows or documents as well. There's that cut, copy, paste function. You know, we're familiar with Control C, Control V for the copy and paste. Scrolling, you know, scrolling up and down within a document. And then word processing functions, you've got your menu bar, file, edit, view, insert, window menu, all of those that allow you to look at and view and make edits to your document, creating a document, printing a document, showing you how to format a document if you're needing to make it bold or highlighted or italicized, you know, all of those changes that need to be made. Presentation platforms. So there's different presentation platforms. Of course, one in particular I use is PowerPoint. You know, that's the most popular, most common one. There's Prezi, which is gaining a lot of popularity. As said here, there's others as well that help you create presentations, whether online or hard copy type. Okay. The internet, of course, that's a gigantic international network connected by millions of servers. World Wide Web, it's the user-friendly format for the internet pages. So all the URLs usually contain one of these: HTTP, www, or .com, .gov, .edu. So those are some common addresses. Accessing the internet requires an internet service provider, of course. Surfing the internet, you know, is just about looking at many different websites, jumping from one to another in search of a particular topic. Your home icon is always going to return you home. And then information sources, there's tons listed, of course, as we know. We can surf the internet, we can create favorites, bookmarks, and even a history. We can import photographs and drawings into documents from the internet. There's text steps in the textbook you can refer to. If you need to do an internet research, just type in the keywords or phrases, you know, associated with your topic. You can use shorter or longer phrases. But you have to be very aware of like the intellectual property and plagiarism if you're using it for a presentation. Perioperative electronic communications. So they're an assigned email, which employs the symbol @ You know, these are going to be monitored by the corporate IT. So you're only going to use your work-related email address for work-related communication. You want to make sure that you're not using the facility electronics and the facility email for non-work related communication. EHR, so these are electronic health records. You'll hear it called EHR, EMRs. electronic medical records or electronic health records. So these are health records that are held within electronic system. They can be transmitted between providers and between facilities to share the information for the continuity of care. Also in scheduling patients, that is streamlined, definitely because of computer technology, allowing things to be seen in all the ORs and throughout the dates, to be able to do that a lot easier. Patients can communicate either through email, faxes still being used, the schedules are able to be scanned, saved, and sent as email attachments. So that has really been helpful in allowing surgical scheduling to be done more efficiently. Let's talk about preference card, and I've got some here for you. This is a digital preference card. You can see in the background of this one is kind of the older model of a hard copy of a preference card compared to the newer ones, either on a tablet. There are a lot of them on a phone. This is kind of a standard of what's going to be on a preference card. So of course, a preference card is the surgeon's instructions that's going to be provided prior to the case. So you're able to know the position, the glove size of the physician, the position. So here, this one's reverse Trendelenburg, rotated right side up, tuck the left arm, the prep, non-sterile prep, and then the notes, blades and sutures, equipment, inventory, everything that you're going to need to be able to pull for this case. Here you can see on this one, doesn't like tape on incision, likes purple. I can't read it all. Arm boards, the procedure's breast. You can just see there's just a lot of different information on here. Sterile processing. So the computers have really kind of cut down on the paperwork that's going to be handled with all of the documentation needed for the equipment. So just like your doctor's preference card are going to a lot more electronic, so is sterile processing's documentation. In addition to all of that, and it will look similar to this one if your facility has that. Competency training. So there's a lot of competency training that's done online. It just makes it easier for the employees and the facility. And those CEs are going to be tracked electronically. There's all those pictures of that. Okay, let's jump into electricity. I hope all of that made sense to you. We're going to first talk about the basic principles. So the electron theory. So this is really the principles that govern the behavior of electrons and electricity in general. And we're going to talk a little bit about matter and atomic particles. Of course, matter is anything that has mass and occupies space, and it does consist of atoms. So atoms are composed of really small particles, protons, electrons, and neutrons. You can see here in the center, in this nucleus, you've got protons, which are your positively charged, and your neutrons, which are neutrally charged, so they have a zero charge, and then your electrons on the outer rims, which are negatively charged. So you have positive charged protons, negative charged electrons, and neutral, no charge on the neutrons. So this creates that polarity, that push-pull that holds things together. So this creates an atom. And these free electrons moving around the nucleus is what attracts atoms to each other and allows that interaction to occur. And so electricity is a lot of these, a lot of that interaction. And so there's some things that we want to talk about because they're really important when we're looking at the surgical cases. So conductors and insulators. So conductors are the materials that inhibit the flow of the electrons. So those electrons on that outer rim, you know, they are going to be attracting to each other, and they're going to be creating a flow. And so it's going to be usually going from the positive to the negative, or the negative to the positive in some cases. But some examples of things that will interfere with that is copper, zinc, brass, and iron, and water. So looking at humidity. Things that insulate. So these are, and this is, hold on just a minute. Let me stop this share because this is incorrect. Let me jump over to your book because I'm like, that's not correct. Let's get to the electricity really quick. Conductors are actually inhibitors will inhibit the flow, but just a second. So we're talking on page 102. Oops, sorry, I thought I was still sharing. Okay, as you can see here in the book, conductors are materials that allow the flow of free electrons. So let me correct this right now so that you have it in your updated PowerPoint. So conductors, materials that allow the flow to occur. So copper is a great conductor, where rubber and plastic inhibit the flow. So those are insulators. So they'll like insulate that to really keep that flow from being free flowing. Some examples of conductors. So remember, they allow the free electrons to move freely through a solid: copper, aluminum, gold, silver, iron, bronze, brass, steel, graphite, concrete, mercury. And you can see these are usually encased inside a plastic insulator, such as glass, plastic, rubber, quartz, a lot of different ones, air, wood. All of these are going to limit the movement. So you've got a conductor encased inside an insulator a lot of times, and that helps to regulate the flow, so that it's not just a open free flow. And so that electrical current, as you can see here, it's going to go from a negative to a positive, in this case through a copper wire. So that current is that movement of the electrical charge. And then of course there's the magnetism and electricity as well. These are created by those electrons that are orbiting the nucleus that I showed you the picture of. And we look at these with heat, with gas, you know, solar and hydroelectric both. In the magnetic fields, the atoms are creating two poles. And so that is creating, you know, like you can take a regular magnet and there's a positive and a negative to that. So if you're taking two positive ends and trying to push those magnets together, they're going to repel. Those electrons are pushing against each other. They're not attracting each other as they would if you flip it. And so then the negative to the positive, you can get that magnetic charge. And here you can see these are magnetic fields. This is a bar magnet. This is south and north. Here's a horseshoe magnet. You can see how the charge is going. And here is the electromagnetic field. And this is really important that we're going to talk about how the electromagnetic field is going to play a role in not only your surgical case, but it also plays a role in just everyday life. So here you can see, this is what I was just talking about. Unlike poles will attract. So you can have the south connected to the north and you'll get a strong attraction there, where if you're doing like poles attracting, they're going to repel each other. North and north together is not going to be a good attraction. So, and this is pretty much what we were just talking about, but metals that become magnetic when a conductor is wrapped around them, and that's like a generator. That would be an electromagnet. And then the electrical circuits, this is the path of the electricity from the energy source to the device and then back to the source. And I'm going to show you a picture of that. Got to correct this really quick. So let me see here. Got a picture. Oh, what did I do with that picture? Oh, it took it away. Sorry. I had a picture of, and I may have it at another point in this where we talk about the ESU. So we'll see if it's there. And then of course, then voltage, voltage is the potential energy of those electrons at any given time between 2 points. And so this defines that electrical potential. So when you talk about how many volts something is, that's the amount of energy that it can put off at any given time. That's the potential of it. And you'll generally see 110s used in the OR and then some 220s. Now, the current, this is measured in amps. And so this is the flow of the electrical charge or the rate of flow. So it's like how fast is it going? And then we talk about power, load, and switch. So power is, we talk about it in watts, like a 75-watt light bulb. So that's the rate and how the work is done. Then the load is how that it transforms that energy into a useful function. So it's able to turn that electrical energy into light. And the switch is the device, of course, that opens and closes a circuit. And as I said here, the wall outlets in the OR are usually 110 volts with those 3 prongs. So you've got a positive, a negative, and then a ground at the bottom. Now we have 2 different types of currents that we use. One is a direct current, and we know these as DC and AC. And DC is the direct and the AC is the alternating current. And so the DC just means that it goes in one direction from negative to positive. Where alternating, it means that it can flow in one direction, but then it can also reverse. So it can be alternating positive to negative or negative to positive, where direct goes from negative to positive all the time. Radio frequency, this is about waves, so frequency waves. And so the frequency depends upon the numbers of waves per seconds. And then isolated power systems in the OR. So here we have different types of a lot of electrical usage going on. And so that's always monitored, because we don't want to overload a system and cause a fire. There is a panel on the wall in the OR, and there's red and green lights on those that continuously give like that electrical circuit status, so that is able to be monitored. So the electrical surgical units. So we're talking about your bovies here. And so this is that electrical current through tissue, and it provides the ability to, as we know, cut tissue as well as coagulate tissue. So these are really important. We use them all the time in the OR. There's several components to that you need to be aware of. We have the generator that is providing that energy, the active electrode that is used to actually incise or coagulate. Then the patient is part of that circuit, and then the dispersive electrode. So we'll talk about that. We have 2 different modes. We have a monopolar mode, so that is it's going in one direction basically, and that is more for coagulation or cutting. And it's used more for cutting. And then the bipolar, and that's not used very much. This is a really delicate one because it's both poles being used there. But it can be used for coagulation, but it's a really delicate use. So here with the monopolar, we've got, again, some of those same components. the generator, the active electrode, and then the return electrode, which is your grounding pad. And that's going to be on your patient's thigh most of the time. And we do have a picture of the ESU. Okay, let me go back. It's in the book then. Give me just a second to find that, because I was looking at it yesterday when I was creating this PowerPoint. So there's your flow. That's your electrical flow there. That's your current. Let's get through the magnetism. There's the ESUs. There is your, there's an ESU itself. Let's look at the circuit, because this is really, this is important for you to be aware of the circuit so that you can understand kind of how the patient is playing a role in this. Here we go. So here you can see the grounding pad is basically where the circuit starts to a degree, and that is able to, and this is a monopolar, and so the energy is going, you know, from the electrode, from the ESU to the patient, to that active electrode. Let's see if they have a, oh, they don't show one of a bipolar. I was looking at that online. Sorry about that. So you can see that the patient is part of that pathway as well. So, you know, it does have a control panel on the generator itself, which is the unit device. And so there's different types of tips that are going to be used on that Bovie, and then that grounding pad has to be properly placed. And like we talked about last week about how that pencil needs to be replaced in that carrying case, so to speak, so that it is not accidentally engaged and causes a fire or cuts tissue that is not needed to be cut. So here we've got the electrocautery. So again, like we talked about, it's used for coagulation, not cutting. Is this one. This one is just a cautery. It's basically called a cautery gun or knife or pin. Same concept as the monopolar. It's just a little bit different configuration. And then that bipolar current, this is the flow coming from the generator to that active electrode. And then the electricity delivers the coagulating current. That current passes through the tissue, and then the current returns to the generator. A big advantage to this, it really does help reduce blood loss, because bleeding is able to be really quickly controlled with that pin as an artery or vein is severed to get into an area that's, you know, that they're working toward. They're able to immediately cauterize that vessel so that the blood loss is greatly decreased. It does save time. It's faster to use this. The cutting current burns the tissue as it divides it. And so, as we talked about, there's a lot of plume as well. You know, it stops and controls that bleeding. It seals a lot of small spaces in tissue and lymphatic tissue vessels as well. And so this helps with that oozing that would happen post-op. So that's really reduced a lot of those complications that we used to see as well. There are some hazards to the patient and the surgical team though, because just as we talked about, there's a higher risk of electrical burns. So we're looking, the reasons for that, the radio frequency coupling, and that's those alternating currents traveling from that active electrode across the insulation and into the skin. And so there's that coupling that, you know, is the part of that electrical current that's going that can cause the burn. And then the dielectric breakdown. So those high voltage currents that are going through can sometimes break down the material, the insulating material. And so then you've got that flow going through faster, and then it's even a higher voltage. And then as we've talked about again, then we've got the tissue plume And so that that tissue, like it says here, is thermally. So the heat destroys it and then it vaporizes it. And so that vaporized tissue could be a hazard to both the staff and to the patient. So that's what we were talking about with those exhaust device. Ultrasonic energy. So this is what's called a harmonic scalpel. Let me look. I had a picture of that as well. Let me look at this. There. Okay. It's like I knew I had a picture. So this is a harmonic scalpel, and you guys have seen these ultracisions made by Ethicon. We've got some of these in the lab. So this is considered a harmonic scalpel. So this is placed over the tissue, and then the clamp part is pressed, and these two teeth come together, and it provides that cautery or tissue cutting. And so you'll see a lot of these done in endoscopic cases. A grounding pad is not necessary on these. These are also used in neurosurgery. They're used in a lot of surgeries, but the harmonic scalpel is really used in neurosurgery a lot. Plasma vaporization. This is used for BPH, that benign prostatic hypertrophy or hyperplasia. And so what it does is it vaporizes the tissue. So you have this button-shaped device, and so this will be inserted, and this will go in and actually start to vaporize some of that hypertrophic material of the prostate gland. And so this is the device here. So this is the plasma vaporization tool. And then we also have the laser, and we talked about this last week. We're going to talk about it a little bit more this week. Laser stands for light amplification by stimulated emission of radiation. There's several characteristics of laser light. There's monochromic. And so we could look at red light versus blue light versus green light and the different components of that. But monochromic just means that it's one color being used. Collimated and coherent. So here you can see collimated just means that they're running parallel, and coherent means that they're running in the same direction. And so here you can see these are coherent. So they're all running in the same direction, and collimated, so they're all parallel. These are running parallel, but they're not running in the same pattern. So they're not coherent, but they are collimated. And here you've got, these are collimated because they are all running parallel, but they are not the same wavelength. So they're not monochromic. So they're bichromic here. So you've got, this actually looks like a trichromic because this is 3 different wavelengths. And then these are coherent because they're running in the same direction, but they're not really collimated because you can see they're not really parallel. This one is going down, this one is going up a little. So that's what that all means. Then there's 4 interactions that lasers have with tissue. Absorption, of course, the tissue can absorb the laser, that laser energy. And then and that tissue is then destroyed, and then transmission can be where it's actually transmitting it. And this could happen when you're looking at it transmitted from one tissue to another, and it can be good or bad. And then reflection, sometimes you can have reflection is kind of used so that precision is there. So they can reflect a laser off of one tissue onto another. But reflection is also something that could be basically like a side effect, you know, and something that could be an error. So it can work in both ways. They can use it, they can use reflection to get to the specific material desired. Then on another hand, reflection can be something that is an actually error in the case. And then scattering is where the laser is actually, the beam is scattered, and then that can cause damage as well. The laser parts, let me look real quick because I was thinking I had you, yeah, I do. There's a few parts of the laser. There's the pump, which is the source of this excitation of the laser beam, the laser head, ancillary components, the control panel, and then the delivery system. There's a couple lasers we're going to talk about, the CO2 lasers, and then in the YAG and the holmium lasers. So the CO2 lasers, these are the most frequently used. This gives really precise cutting, and because it's able to absorb that energy with the water content, so coagulation and cutting both are very precise. Where the ND YAG and holmium lasers, this is a pulse beam. And so with this one, I was going to look and see these here. Okay. All right, this is the CO2 laser here in the upper left-hand corner. Oops, sorry. Okay, this is I think this bottom one is the YAG, and then this is the holmium, because the holmium is used more for like lithotripsy. And so that is where you're looking at getting that pulse beam, because we've seen a video at some point in the past, and those of you that haven't yet, when we're talking about kidney disease and like kidney stones and how that is treated, we'll see that lithotripsy, and that uses this holmium laser where it's providing a pulse beam. And it does go through like a flexible fiber that can give that, that wave pulse. Okay, and here you can just see this is the different particles that it consists of. And then we have a krypton laser. So this is using a gas, and it is an electrical current that activates the krypton gas to create a laser energy. And then the exciser laser, this is halogens and gases both. And so this is easily recognized by, it's a ultraviolet in color. And so that's a purple beam that we see. And here we can see there you've got a krypton here, and lost the word, exciser. So the excimer, both of these are used in eye surgery a lot. So corrective laser, you know, so they can use a laser to correct the vision. So this one is the krypton, and this is the excimer used in laser surgery. So the krypton is used, as you can see, a little more outpatient than the excimer. And then the argon laser. So this is a blue or green light, where that plasma tube contains argon gas. And then we have a lot of different types of cases that these lasers can be used in. So GI endoscopies, laser micro laryngoscopes and bronchoscopes, stereostatic lasers used in endoscopes, arthroscopy. So we're looking at joints with the laser and doing laser corrective surgery, endoscopic transurethral prostatectomy. So those are a lot of the cases that you may see. Here again is another, that one is the krypton, I'm pretty sure. Okay, natural body orifices. This is where a lot of portals are used for diagnostic and surgical treatments. So thinking of, when you think about natural body orifices, these are orifices that already exist. So we have oral, vaginal, rectal, penile, you know, so opening in the nasal eye, ear. So these are ways that the existing orifices can be used for diagnostic and surgical treatments. I'm thinking of endoscope, resectoscope, hysteroscope, and notes. You can think of notes being the key acronym for natural orifice transluminal endoscopic surgery. And then we can do transcutaneous access. So this is through the skin. So here we're using things like trocars, I'll show you in a moment, as well as insufflation needles. And so these are some insufflation needles. You can see they have a stopcock on them so that the CO2 gas can be injected into the cavity to expand that cavity so that there's a lot of visual space there. So these cannulated needles, you can see, can be inserted into the cavity. The gas can be added, and then stopcock switched it off and allows for a much better visual field. Trocars, here's the insertion of all the trocars. This multiple varieties you can see here, including sizes. So there's different types. There's a sharp, there's a blunt, there's dilating, there's single ports and multi-ports. In these, there's the outer sheath, there's the inner sheath or cannula, that inner obturator, and we'll show you all of these. I think I did a picture, yeah. And then the valve mechanism, and then the stopcock valve, which we talked about. We did already talk about the distension method, one of those being that insufflation, peritoneal cavity insufflation. We could also do mechanical distension, which is not as effective, but that's just mechanically distending the belly to move it out of the way. Fluid distension methods as well can be utilized, but the CO2 is the most common now. So here is a trocar. They're in multiple sizes. You can see this one is 11 millimeter. There's 12 millimeters, 5 millimeters. We have a good variety in the lab. There is a seal here, that will seal nothing from coming out. A cap that can be detached. Here's an obturator, and it's usually clear so that pathway can be seen. And then there's an anchor here and a balloon here if that's needed to be inflated to allow the trocar to stay in place. Visualization, so what it does is it allows minimally invasive surgeries to occur, which are called MIS. And so it allows for that visualization, the trocars and endoscopic tools. And so it allows the physician to really clearly see that operating field. So we have those sterile endoscopes, and that gives lights. And then, we've got the fiber optic lights inside that sterile, inside that visual field, cameras. So we're going to have a lot of accessory cords and cables and all of those things, TV monitors, the light source and cameras and all that go along with it. So there's a lot that go with the endoscopic surgery, but it's very effective and minimally invasive. So where in the past, or even now still, if an example is open appendectomy compared to a lap appy. So we've got a lap appy where we've got 4 puncture wounds of 4 different trocars compared to an incision and an open case. And so there's a lot more risk involved with an open case compared to trocars typically. So endoscopy is becoming much more common these days than open cases. Now let's talk about robotics. So these are really becoming common, especially in certain areas of surgery. It's a very sophisticated machine. It's able to perform very specific tasks. There's mobility degrees, they're programmable. It can operate automatically and do a lot of different things. There's first, second, and third generations of these robotics. They have definitely improved patient care, and they've helped control the cost of healthcare. So there's some terminology that you want to look at on page 115, just to get familiar with some of the terminology around the robotics, because there's a lot of use of these days. You know, knowing what the manipulator is, you know, and what the resolution means, because you'll be able to help your physicians set these up. The Da Vinci robotic system is one of the most frequently used surgical robots. There are some pictures that you can look at in the book of these robotic systems. There's a console, there's a patient side cart. There's usually 4 manipulators that are able to do the work, and then a vision system. So the physician is in the assistant and tech are able to watch what is going on. Now, one thing that's, well, I think it talks about it later also. And your role in this is you'll be positioning that system. You'll be connecting the cords and the equipment, testing the system if needed, loading and switching out the surgical instruments on those manipulators, which are basically the doctor's hands in those robotic cases, and then troubleshooting any situations that come up. And these are some of the major advantages. Hand tremor is something that's really problematic in surgery. And so, especially when we're looking at doing really precise surgical techniques, such as neuro and microvascular. So the robotics have really been able to come in and provide very stable and precise techniques where hand tremors would always be a problem. And those really complex interventions that were needed in really confined spaces, like the microvascular and neurosurgery, it allows the robot to go in and do that microscopic work. And then there is a much better visualization of using the robotics and 3-dimensional imaging used to accomplish that. And it also allows for telesurgery. So this is where you could have a device at a small hospital and the surgeon could actually be performing it at a remote location. So not at the location of the surgery. So it's been really a big benefit to small hospitals. And here are some of the manipulators that you can see. They're categorized by geometrical design. And so these joints are going to be referred to as like the elbow or the wrist or the shoulders. And so, you know, you can see there's going to be, with different types of manipulators, there's going to be different degrees of rotation and freedom. So there's different geometry designs here. As you can see, the Cartesian coordinate geometry, cylindrical, and the revolute geometry. So different types of those. Then there's a voice activated control system, and this is hearing and vision. So this is where the robots can actually be activated by the surgeon's hands moving on those manipulators, or a voice, you know, by that either headset or microphone. So it's a way to control the manipulator and different other applications. The great thing about these is there can still be casual conversation going on in the case that is going to be ignored by the computer. So, so it's really sensitive. So it's a really important part of this. Here we have different types of robotics and guided imaging systems. So the Makoplasty, this is the one that's used for knee arthroscopes. Rio Robots system for hips. Orthopilot is for like a total joint arthroscopy. And then for neurosurgery, we've got Neuromate or Stealth Station. And then sinus and anterior skull base. These are fusion ENT navigation systems. So just some different types. And then there's a lot of hybrid suites design that's going on. So this is where you've got a little bit of everything. You've got surgery, radiology, guided imagery, all of it happening at once. And so some of those cases where you would see a hybrid type of OR, endovascular aortic aneurysm repair. So you may have a lot of these different components transcatheter aortic valve replacement, coronary artery vascularization, atrial fib ablation and pacemaker implantation, cranial and spinal angiography. So these are where a lot of these things are merged. Okay, so hopefully in this chapter, you've been able to learn about the basic computer systems, computer knowledge as it relates to the patient, electrical safety, the basic principles of electricity, electrosurgical units, alternative energies, and then the basic concepts of robotics. So I hope this has been helpful to you all. If you have any questions about chapter 6, either your homework, and I've already requested that Nawana send chapter 6, the chapter itself and the homework to you guys. If you have any questions, any concerns, don't hesitate to let me know. So I'll get this recording loaded up as soon as it's ready, and because it'll take a little bit to convert it, and then I'll get it loaded up on YouTube. So thank you. Oh, I forgot your, I keep forgetting that. So, you know, I'll look around then because I forgot to insert that. CPR class. I want you to mention that we are working on getting CPR class and to the end of the term. So you can just say CPR class. So thank you, and let me know that magic word.